Hi students, this is a video taking a look at oxygen and its configuration and how it interacts with other elements and its importance in the universe. All right, so we are looking at oxygen. This is the 8th element on the periodic table, with an atomic mass of approximately 16. So what does this tell us? This tells us that there are 8 protons and 8 neutrons. And we're going to be looking at the Bohr model of oxygen. There are more precise models available, but they're very complex, and for high school chemistry, I don't know how useful they are unless your teacher is actually testing that. So in the first level, the first orbital of oxygen, we have 2 electrons. I like to draw them on opposite sides when I can to suggest that, given that they're both electronegative, that they would repel each other, so they want to be as far away from each other as possible. So in the first orbital, like in every element, we have 2 electrons. That means that we have a total of 6 electrons left that we need to account for. So I will place them more or less as far away from each other as I can. So this would be the typical oxygen atom in its pure form. Now, this is not the only version. There are 2 other stable isotopes of oxygen. This is something along the lines of 99.97% of oxygen is found in this oxygen 16 form, meaning that the atomic mass of it is 16. But we do have oxygen 17, and we have oxygen 18. These heavier isotopes exist, and they would be in the form still same number of electrons, but an additional neutron. These are relatively stable. There are actually other isotopes. I believe it goes from something like oxygen 11 to oxygen 25, but the other isotopes are not stable. They will decay fairly quickly. The percentages, they're actually almost the same. I believe it's 0.02% and 0.03%. I feel like that is less important for this analysis. So I want to talk about a property of oxygen. This particular property is known as electronegativity. But before I get into the technical details, I want to talk about this idea of collecting. I think this analogy is very helpful to understand why oxygen operates the way it does in the world and in the universe. So I have collected lots of things throughout my life. Probably a little bit too old to admit this, but in my late teens and early 20s, I collected Pokemon cards. And as the saying goes, you gotta catch them all. So I don't know about you, but if you've ever had any collection, you don't feel satisfied until you have the collection complete. So let's just imagine that in my Pokemon collection I had 140 of the 150 original Pokemons. I'm not interested in the other 1,000 some odd or however many they have nowadays. Talk about the original deal. So if I've got 140 of the 150 Pokemon, how would I feel? Well, I would feel unsatisfied because I want to collect and complete my collection. So as a result, how would that affect my behavior? Well, I would seek out the remaining Pokemon cards so that I could complete my collection. And this is essentially how Oxygen operates. Oxygen, instead of collecting Pokemon cards, Oxygen is seeking to fill its outer shell of valence electrons. So Oxygen will feel complete when it has a total of 10 electrons, 2 in its first shell and 8 in its second. So if you remember, the atomic number of oxygen is 8. It has 8 electrons, but it's seeking to get an additional 2. Once it has that, it will be stable. So it's going to do what it needs to do in order to complete its collection. It's so close. It's almost there. It just needs 2 more to complete the set. And so it will bond in various ways in order to complete its set. It will bond, for example, with oxygen to share its electrons in forming what we call a non-polar covalent bond. That is the oxygen that we breathe. So in this example, oxygen is sharing its electron. It would be as though I would be sharing my Pokemon collection. So I've got a buddy who's missing 2 cards and I'm missing 2 cards. So we would kind of split our collection and each borrow our 2 cards, which is satisfying, I guess. It's getting me closer to having that full set, but it's not really fully, it's not the same thing as being able to have the complete set. So even if I'm willing to do that, I would still be looking around for opportunities to continue to get my set, which is why oxygen gas will readily bond with any elements that it encounters. And so what we see is oxygen is what we call strongly electronegative, meaning it will do what it can to strip electrons from other elements. It is a high level of electronegativity, meaning that it will readily strip electrons from just about any element. And we see this in real life. So if we were to look at, let's say, original penny made of copper, what you often will see is that the bronze color, that brownish luster, has over time turned into a kind of greenish white color. And that is a result of oxygen stripping electrons from the copper to form what we call copper oxide. That is actually also that is why the Statue of Liberty has that green color as opposed to the original copper color that it had in 1898 when it was constructed.